So, a little bit about COVID-19 growth. One of the best sources of data that I've used for this disease has been the News and Observer, and this is one of their charts that they have on their pages. So, in the beginning of the disease, back in March, when even I was a little bit worried about it in North Carolina, wouldn't be able to get it under control, the cases were doubling every 2 to 3 days. Now, if that kept going, we would be talking about almost everybody in the state getting infected. So, doing the masks at the end of March, social distancing, closing of things, it actually had a great effect on the total number of cases. The red line here represents a case doubling every 10 days, and we've been below that since April, which is really good um, compared to when we started off with doubling every 2 to 3 days. So right now we are doubling every 31 days, which is actually pretty good. So one way to talk about the growth rate of something is known as a doubling factor. And I want to show you how dangerous it would have been to have a doubling factor of 2 to 3 days through the summer all the way up to the end of July. Chart. Let's say we have days and number of cases. And I'm going to do a horizontal chart. I usually do vertical charts, but horizontal in this case works out fairly well. So on day 0, let's let there be 15 cases. On day 1, let's double it. On day 2, let's double that. On day 3, let's double that. And so forth and so on. And we can stop there. And you can kind of see that after 5 days, we went from 15 cases up to 480 cases. And that's pretty close to what the data is showing us. All right, so one thing that I can steal from each one of these numbers is a factor of 15. So if I factor this out, it becomes 15 times 1, and then this one is 15 times 2. 60 is actually 15 times 4, but I can write 4 as 2 squared. 120 is 15 times 8, which is 2 cubed. 240 is 15 times 2 to the 4th. And then 480 is 15 times 2 to the 5th. So it's kind of a cool process. Now, another way to look at this, which is much more important for our feature, is going to be, this is 15 times 2 raised to some power. We'll talk about that power in a second. This one is 15 times 2 to the 1st, 15 times 2 to the 2nd, 15 times 2 to the 3rd, and 15 times 2 to the 4th, and 15 times 2 to the 5th. So if we count backwards, 4, 5, 3, 2, 1, this one has to have a power of 0. And a cool fact about math, anything raised to the 0 power is equal to 1. All right, and notice that the powers are matching up with the numbers of days up above. Power of 1 down below, power of 2 up above. Day number 4, we have a power of 4. So this generates an idea of what's going on here. Now this is doubling every day. So if I made it double every 3 days, we would still want the powers to go 0, 1, 2, except they're happening every 3rd day. So here's a chart describing doubling the number of cases every 3 days. And notice that not a lot changes for the number of cases as long as I'm counting by every 3 days at the top. It'll change a little bit if I look for 1 day or 2 days. And it becomes a little bit more difficult to talk about, but if we come up with a formula, we can pretty much approximate what's happening in between. So again, this is going to turn into 15 times 2 to the 0, the same numbers as before. Oops. 2 to the first, 15 times 2 to the second, 15 times 2 to the third. So, unlike the last table, though, the numbers aren't matching, well, except for the 0. The 0 matches rather nicely, but 0 is kind of boring. So this 3 has to be turned into a 1. The 6 has to be turned into a 2, and so forth and so on. So we can calculate this out with a formula. So what's really going on here, if you kind of think of, what can I do to 3 to get to 1? What can I do that's exactly the same to 6 to get me a 2, and so forth and so on? It sounds like I'm just dividing by 3. So the formula for this is going to have this format. The future value, number of cases, is going to equal the present number of cases. That would be on day 0, which would be 15. And if you don't see the correspondence yet, this is a lot like dealing with money, because generally money grows. All right, and then we're going to times this by our base is 2. That's our doubling factor. And then we're going to take the number of days that has passed, t, and divide it by the doubling factor, in this case 3. So when t was equal to 15, 3 is the doubling factor. We'd get 15 divided by 3 is this 5 over here. All right, so the specific formula for the one above us is f equals the population started at 15. The 2 remains a constant. I like sometimes putting that in parentheses to separate it away. And then we're going to have the time divided by the doubling factor of every 3 days. So that would be the formula that matches up with this. And now we can start looking for odd days. Let's say day 7. So on day 7, we have to type this into a calculator. So about 75, 76. And that would be between 6 and 9, and that's pretty much, 76 is someplace between 60 and 120, a little closer to 60. So the future value based on this formula would be about 76 people would be infected with COVID-19 on the 7th day after the day 0. So that's the doubling factor formula. So this is the formula that will find us the doubling factor. Now, let's use it to see, I think it's been 126 days since the first case in North Carolina. So even if we start off with 1 case and we double it, and let's say it kept a doubling factor of 3 days, we've been 126 days with a doubling factor of 3 days. So that's 2 raised to the 126 divided by 3 times 1. Let's see here. That's 4.398. 4.398 times 10 to the 12. So if the doubling factor stayed at 3 throughout the entire summer, which is kind of crazy, that would just be letting the disease have its way with us. That would be times 10 to the 12. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if it was just 1 case in North Carolina, and we didn't do anything to stop the spread of this disease, that's hundreds, thousands, millions, billions. You might as well say the entire planet Earth would be infected by the end of the summer. Kind of crazy what a doubling factor will do given enough leeway. And this is why it's really important to have the CDC and the WHO so that we can keep diseases like this under control, because if we let them out of control, bad things are going to happen. so let's break down the formula. F, of course, is the future value, the number after a period of time. P is generally the starting value. So starting value can be, pick a day, how many do we have on that day, and that'll be our zero value. The doubling factor, now doubling factors can be in days, minutes, seconds, years, months. It doesn't matter what the time factor is. But T has to match whatever the double factoring is. So if I tell you the double factoring is every 3 months, and I ask you how many are there going to be in 10 years, you have to change the years into months to match up. So you're always converting time back into the doubling factor. So be really, really careful with that part. So for example, the current doubling factor for COVID-19 in North Carolina is every 31 days. If initially, as in today, there were 98,000 cases, how many would there be in 120 days if nothing changes? All right, so we start off with our formula, and I highly suggest you always write the formula first and then substitute stuff into it. So, do I know the future value? And the answer is no, I'm looking for that. Do I know the present value? Well, 98,000 cases. 2 never changes because we're talking about a doubling factor. So make sure you see this word in there before you use this formula. T in this case is going to be this or this. And that's where a lot of people get confused. So be really careful. The doubling factor for COVID-19 is this 31 days. So that has to be D. And then we're asking, in 120 days, what's going to happen? That is the time that has passed. So this is 120 divided by 31. And then all you have to do is type it in a calculator. Now, a little cautionary tale about calculators. When you type this in, you're going to type in 98,000 times 2 caret parentheses, because 120 over 31 is 2 numbers, and powers can only be 1 number. You have to put parentheses around the calculation 120 divided by 31.
Okay, let's see if my calculator will do this. So, 9800 times 2 raised to the 120th divided by 31.
Hey, it did it. Awesome. So that is 1433,849. It's much easier to write it first and then read it. 0.2, but that's useless. So every third number, a comma. So that's 1.4 million people. So even with this doubling factor a lot smaller than our initial 2 to 3 days, 31 days is still from 120 days, basically 3 months from now, 4 months from now, we'll have 1.4 million just in North Carolina infected with the disease. So we've dealt with exponential growth before, and doubling factor is kind of an exponential growth, but not exactly. So we're going to talk about our compound interest formula one more time, and I'm going to fudge it just a little bit because I don't want to get into the deep math behind it, but I can show you part of it. Let's ignore a few things about this formula. Let's ignore the P, just drop that off, that's always changing. The R is also changing, and T, of course, can be any number that we want. So the important thing, and if you remember, going back into the compound interest, I asked you to change N to be almost, I think if I remember right, up to 1,000. And you saw that the balance wasn't changing much as N increased, and we held the time, the rate, and the principal, the constant as the same. So if I drop all those things, I end up with a formula that looks like this. Now, if you take n and you type in any number that you want for it, and I highly suggest a rather large one, what you'll find, like if you put in 1,000, raise it to 1,000, Now remember, to type this in a calculator, it would be 1 plus 1 divided by 1,000, and then you have to put a caret and then 1,000. And the answer to this, let's see if I have it in my calculator. I do not. Parentheses 1 plus 1 divided by 1,000. My writing calculator does not like large exponents, so I have to do this by the handheld calculator. So this turns out to be 2.71692. And then if I make it 10,000, it gets closer to another number. So same thing, I'm going to do 1 plus 1 over 10,000, just an extra 0, and then raise to something with a 1 and 4 zeros after it. So this turned out to be 2.71814, blah, 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 a lot of other decimals after it. So you can see that the decimals are approaching a specific value. So if I change this to a million, so with a million, 1 mil equal to n, we're going to get 2.71828, and then some other decimals. So this number that we're approaching is known as the natural number. So let's go back up to the top and define it. So there's this fancy little notation. And what it turns into is this number called E, which is really close to 2.71828. Okay, so this is known as the natural number because it naturally shows up when we do exponential growth based on the compound interest formula for n getting really large. So this will be the limiting factor, the maximum amount of money you can make with what's called continuous compounding. And I'm quite sure we talked about this also back when we were talking about compound interest. So that formula is still going to come into play. So that formula was F equals PERT. It had that E in it. So this is continuous growth. And it's a better way to model something because that R kind of gives us the rate of change, a percent per whatever the time frame is continuously. All right. So there's a relationship between this formula and the doubling factor formula. So we can go back and forth between them, and it comes out to be pretty nice. For instance, if we have something like 238 e to the 0.03t. So what this would represent is if there are 238 people, let's stick with my little topic here, COVID-19, that are infected with COVID-19, then this kind of represents 3% growth rate. But it's not 3% per year, even though we could convert it into per year. What it means is it's growing at 3% continuously. So this is 3% continuous growth every second of every day, every millisecond of every day. It's kind of confusing, but it's always growing at 3%. Excuse me. All right, so to change that into a doubling factor, what we're going to do is we're going to use the formula D equals ln of 2 divided by R. And R in this case is the 0.03. So this doubling factor is going to equal this thing on a calculator. You're just going to type in ln of 2, and I'll tell you where it is. And then we're going to divide it by 0.03. So on the calculator, to get ln, you're going to push this button. It's the same one for e to the x, except you're not going to do the second first. You're just going to type in ln. It should give you a parentheses. Put in a 2. Make sure you close the parentheses, and then divide by 0.03. So try it out on your calculator. Make sure you can do it and get this answer. So the doubling factor should be 23.1. Now, if t was measured in days in the original formula up here, so here the doubling factor is not the important part. Here they have to match up with time. So if the time was measured in days in this formula, then this continuous growth would be based on days. And then down here, this 23.1 would represent number of days before it doubled. If t was in minutes, then this would be 23.1 minutes. So the t and this d have to match time frame wise. So let's say this was days up here, then this would be days down here. So we can convert a exponential rate into a doubling factor rate. And this is kind of gives us good information that every 23 days, the growth, the population of, or the number of cases of COVID-19 will double. So there's reasons to go back and forth with this idea. Sometimes doubling factor makes more sense to people. Other times a rate of change of growth will represent something else to other people. So we can also go the other direction. So the formula for the other direction is we're looking for the rate, and the formula looks almost the same. It's ln of 2 divided by the doubling factor. So in this case, the doubling factor is 3. That's that number in the bottom. So we're going to get r is equal to ln of 2 divided by 3. And remember, r is going to be a decimal number, but we can interpret it as a percent. So ln of 2 divided by 3. So if we were going to change this into a exponential model using PERT, then this thing would be f equals 15e to the 0.231t. And here, this is kind of representing a 23% growth rate. You'll see later that we're going to do a model on Florida's numbers currently, and their growth rate has a 0.889, which can kind of give you an idea, 0.889, of the doubling factor they're dealing with right now. So ln of 2 divided by 0.889. Their doubling factor, ooh, it came out a little weird, so I was a little bit leery, is 0.78. So the time frame that it was measured in was days, so they're doubling in less than a day right now, which is really kind of scary. So that's how we can convert between doubling factor and exponential growth. Now, the other direction that we can go, instead of growing exponentially or doubling factoring, then we could have this thing called halving factor. And halving factors, take half of something, is a decay model, because if you keep taking half of something, eventually you'll end up with something really, really small, close to zero. Technically, you never ever get to zero with this model. So it's built kind of the same way as the doubling factor. You're going to have a future value, you're going to have a starting point, but instead of doubling, you're going to be taking half of the number. The power stays almost the same. I just changed the d into h to represent halving. So this halving model works really well for radioactive material, and kind of gives you an argument against nuclear powered energy. But we could also hopefully eventually soon use this to model the number of cases in the United States. We're hoping that after you exponentially grow to a certain point, to turn it around and bring it back down to close to zero. So in the near future, when we start getting a vaccine for COVID-19, hopefully it'll work really well, then this model will kick in and the disease will be what's called eradicated. It technically never ever goes away, There's still the Black Plague in the world, which is really interesting because you always think of that as, 12th, 13th century Europe. Okay, so if, for example, alright, so a radioactive isotope has a half-life of 23.5 years. What does that mean? So that's pretty much what I want to get into. We have 100 kilograms of this stuff. Now, if they don't tell you how much you have or how many people you have, always start with 100 because that can represent 100%, which is kind of nice. So how much of this will there be in 23.5 years? Well, after 23.5 years, we're going to have to take half of the amount. So there's going to be 50 kilograms left. So then the next question would be, well, how much will there be in 47 years? Well, 47 years is just another 23.5 years. So we would expect half as much. So this would be down to 25 kilograms. And then to figure out the next one, which would be 70, 80.5, it would be half of 25 kilograms, which is 12.5 kilograms, and so forth and so on. But if you keep dividing this number by 2, you'll never ever get down to 0 because there will be a little bit left over. So to go backwards and forwards between an exponential growth model and a halving growth model, so f equals p 1/2 t over h, and I want to convert it into f equals pert. The first thing to know here is r is going to be negative, representing the decay that's going on, compared to r being positive for growth rates. So the formula to convert from this side to that side is going to be r is equal to ln of 1/2 rather than 2 divided by h. And then to go this direction, it's going to be h is equal to ln of 1/2 divided by r. So these are the go-betweens between these two formulas. If I give you a exponential function with a rate, then you should be able to tell me what the half-life of an isotope or a disease or a medicine, a bloodstream, by going the other direction. All right, so the next part is how does a spreadsheet work with this data? All right, so let's talk about exponential growth from data. Now, one thing that has to be different, and I found this out the hard way, before with the linear, you could leave these as dates from data, but for exponential, they need to be numbers. So all I did was go through and replace March with 1, April with 2, and so forth and so on, all the way up to July. So we're going to do the same thing. We're going to select our titles and the data. We'll go to our Create a Chart. And over here, we're going to choose Scatter Plot in case it's not chosen already. It is for me because I already created one. And I'm going to have to make it smaller to fit. There we go. Now these numbers are Florida's cases, and you'll see that they seem to be growing exponentially here. So to get the trend line in, if you lose the picture, just double click it. Over here to the side, choose series. You might want to change the size of these points down to the smaller version. If not, you don't have to. My next example, I'm going to have to because they're North Carolina gave more data than Florida did. Literally, the only data I could find for Florida was monthly totals. All right, and we're going to go down here to trend line. I'm going to change the color of the trend line to be something different. And we're going to choose linear. Now, if you look at linear, this one's above it, these two are below it, this one's above it. So you could approximate it using a linear equation, which is fine, but I'm pretty much guessing that this is closer to an exponential. So I'm going to go up here and choose the type as exponential, and you'll see the points lie closer and closer to this line than they did the linear line. They're further away here. So the better model for this case is exponential. Now, one thing to notice in this model is the exponential decimal. This is like 89% growth rate per month. Kind of scary. So let's compare that to North Carolina's. So I already did North Carolina's, and it looks like this. It gives us a lot more data to work with. And you'll notice that the exponential exponent is only at about 3%. So Florida's caseload is increasing at 88% continuously right now, whereas North Carolina is only growing at 3%. So that's why North Carolina is in better shape than Florida is right now. So that's how spreadsheets are useful to analyze information.